The Best of Our Knowledge explores topics on learning, education, and research. Coming up, Einstein theorized that at the center of a black hole, the laws of time and space break down. But quantum theory might allow researchers to further our understanding of the unknown. And an underground water source that feeds rivers in the Pacific Northwest could be much larger than previously thought. I'm Lucas Willard, host of The Best of Our Knowledge. You're listening to The Best of Our Knowledge. I'm Lucas Willard. The center of a black hole, as theorized by Albert Einstein, is inescapable. It's also where our understanding of the cosmic objects comes to a dead end. The singularity, where the laws of time and physics break down, is also a mathematical roadblock. But quantum theory, applied to a simplified model of a black hole, could give scientists a better understanding of what happens at the center of a black hole, and how they could represent not an end, but a new beginning. To learn more, I spoke with Stephen Gielen, a senior lecturer at the University of Sheffield.
Black holes are very extreme objects. So, we have a great theory of gravity, which is Einstein's theory of general relativity, right? Which, as far as we know, has been proven to be correct by many different types of observations. And it makes these very radical predictions about the nature of space and time. And it does predict that there should be objects that are black holes where basically the gravity is so strong that nothing can escape anymore. And time, in a sense, basically comes to an end inside the black hole. And that's very radical, but it also means that basically the theory breaks down entirely. Once you're inside the black hole, at some point there isn't really a way of predicting anymore what actually happens. So it also gives you this window into something else, right? Because that theory is incomplete, it tells you that something else has to extend that picture. So that's really where my motivation for this research basically comes from, to understand kind of how we can use these predictions just from general relativity to understand maybe what lies beyond.
And that point in time or point in space in a black hole where things do break down, that's called the singularity. Am I correct?
Yeah, that's right. We call that a singularity. That's right. And it really just means that everything breaks down. Yeah. So whatever you would want to calculate basically just comes out as infinite. The gravitational force would be infinite. The energy density inside the black hole would become infinite. So that's really just where our description ends.
So you were motivated by thinking, okay, well, what if? What if there's something different inside of a black hole where things don't just come to a complete stop, where time ceases to exist? So where did your theorizing and your math begin in this situation to help maybe theorize, well, maybe there's something else there?
Mm-hmm. So I think many of us believe that the reason why sort of general relativity breaks down in these extreme situations is that it doesn't include quantum mechanics. So it's a classical theory, it's a deterministic theory, it's not compatible with the rules of quantum mechanics. So we are really looking for a more complete picture that includes both quantum mechanics and gravity, which is called quantum gravity typically. And so for me, that's the natural starting point to basically include sort of aspects of quantum theory, things that we think we understand from other situations in quantum mechanics, and basically see what, if you take those assumptions seriously and you apply them to that example of the black hole, how that picture would change. And it might tell you something new beyond sort of the classical description.
Would you be able to maybe back up a little bit and tell me how quantum theory and quantum mechanics, how this theory differs from Einstein's theory of relativity and the arithmetic and the math that Einstein used to come up with his theory?
Mm-hmm. So yeah, so if you're asking about the mathematical structure, they're really very different. So in Einstein's theory of general relativity, we're thinking of space and time really in geometric terms. So we're thinking of space-time curvature. We're thinking of sort of space and time kind of bending under the influence of objects in the universe. And basically, if you're experiencing gravitational attraction, this is explained by basically a curvature in space-time. But the theory is also deterministic in the sense that, if you have some system and you know everything about the system, you'd always be able to predict what happens in the future. And in quantum theory, that's all very different. So in quantum theory, we have an object called the quantum state, and for any system that you're interested in the lab. And the quantum state always contains different possibilities at the same time. So there's basically sort of multiple possible outcomes are encoded in the quantum state. So once you make a measurement in your lab, you will actually find one of these outcomes with a certain probability, but you don't know exactly what you're going to find. So you can see that sort of the fundamental structure is already very different, even on the most basic level. And I guess another difference, which is the one that we're actually exploiting in this work, is the difference in the nature of time. So this is maybe the most important one. So in general relativity, time is not an absolute concept. It depends on where you are and how you're moving through space-time. You will experience time in a very different way. Whereas in quantum theory, in a sense, to define your theory, you need to have some reference time. You need to know how things evolve in time. And that is not really dependent on the observer in the same way that it is in relativity.
The research suggests a difference from a transition, as it's put, to a white hole, different from a black hole, but a white hole. Can you explain what that is and what is the idea behind a white hole? Because I think a lot of people have heard of the black hole. They've seen movies and TV shows, but this is new to me.
Yeah. No, that makes a lot of sense. So the white hole, so the black hole is, as I said, is a prediction of general relativity, right? So this is this kind of extreme object where all the mass that maybe, once was a star has collapsed, and now it's sort of this super dense object which has these very extreme properties. So that's a prediction of general relativity. And the white hole is basically the time reverse of the same situation. So in the black hole, basically the defining property is that you have, this kind of surface, which is called the event horizon, right? And as you fall in, once you're past the event horizon, you can't get out anymore. You're basically trapped, and you will always end up in the singularity, no matter what you do. This is unavoidable. So the white hole is basically the same thing in reverse. So you will then also have something like the event horizon, but it has the opposite effect, which means that, if you're inside, you can only go through the event horizon back into the outside, right? So it's again like a one-way street, but now the other way. You can only get out of the white hole, but there's no way of actually getting in from the outside. So because the equations are actually, this is true for all of physics, you can always play the movie backwards and you get another solution, right? The equations are actually invariant if you change the flow of time. The white hole is actually a perfectly consistent solution, even in normal general relativity. The reason why it's not taken seriously usually is that there's no process of creating these objects. So there's no process in which they can be formed. So there are theoretical solutions, but they can't be formed from stars or other objects in the universe. So they're not taken as physical in the same way.
So it's not then if a black hole gets too filled with stuff that it reverses and becomes a white hole, is what you're saying.
That's not the case in general relativity. So in general relativity, the size of the event horizon is directly determined by the mass that's inside, which means that if more stuff falls in, the event horizon will just keep growing, right? So the object will just become bigger and bigger and bigger. And there's actually no way of reversing that process. So a black hole, at least classically, can actually not shrink. It cannot lose any of its mass. It can only acquire more mass.
How does this theory then change or alter our perspectives of what we understand about the universe?
Mhm. So, I mean, I have to say, of course, that what we're studying is a simplified mathematical model. It's not a realistic model of a black hole. I think what it would suggest, I mean, in the first instance, it would suggest a different picture of what happens once you're actually inside the black hole. So if you actually an observer that's falling into the black hole, normally you would just expect to hit the singularity, but now if this quantum picture is correct, then you would actually end up in this transition and you would end up in the white hole, which means that basically you come out on the other side and it's basically like another universe, essentially, right? Now, the question, of course, is what that means in terms of actual physical observations. So, for example, these observers could be, for example, just signals, sort of light rays, any kind of signals that would, in a sense, be able to make that transition and come out on the other side. Um, so in that sense, it's kind of certainly a different perspective on what happens to stuff that's inside the black hole. Um, Now, of course, the model, as I said, is very simple. Um, so it would have to be refined a lot more to be able to actually describe a sort of astrophysical black hole and one that's actually observable in our universe. So one thing I think that's also mentioned in the paper is that this model is a simplified black hole in the sense that it has so the event horizon is actually not spherical, but it's kind of flat. It's more like a plane. Whereas for a realistic black hole, you would expect it to be spherical. So that's one way in which we simplified the analysis.
I see. So and a lot of people, maybe because of science fiction, as I had mentioned earlier, think of what a black hole might look like. You picture that round ball
Mhm.
floating out somewhere in space where everything is drawing into. But this is more, as what you're saying, a planar black hole where it's on a flat plane where this is theorized. Now, do you think that this research could point to any ways of then observing this or proving the existence of a white hole? It wasn't too long ago that scientists were able to generate that now famous image of the black hole. And do you think that from this kind of research and quantum theory that there could be a search for a white hole in the future as this becomes more refined?
Yeah, absolutely. I think that's certainly, I mean, that's a more longer term prospect, but I think that's certainly something that would be very exciting because, I mean, basically, as I said, I mean, the white holes have always existed as, abstract mathematical solutions, but we didn't take them seriously because there's no mechanism of forming them. Now, if we think that quantum theory leads to a transition of a black hole to a white hole, that would be a mechanism of forming these objects. So then there, would be reason, at least in principle, to imagine that they're actually out there in the universe. Um, so that is definitely a very exciting prospect, absolutely.
And Stefan, where will your research take you next?
Right. So, I mean, this model is very exciting, and we just have to make it more refined and more realistic, right? So, I mean, the next step, which is work that we actually already have now, is actually to make the black hole spherical, to make it more realistic. One limitation of the study is also that the black hole, as we describe it, is a so-called eternal black hole. So it's just something that sits there with a fixed mass. It doesn't interact with its environment. It doesn't, accrete mass from the exterior, and it also doesn't radiate. So black holes usually expected to radiate through what's called Hawking radiation. So they would actually also lose mass. So there are these dynamical processes that actually change the nature of a black hole over time. And of course, including those is, much more difficult, as you can perhaps imagine. It makes the model much more complicated, but it would make it more realistic. And so those would be very interesting developments because they would, then you could ask the question of what happens to those dynamical black holes.
Is there anything else that you'd like to mention that you do think that we may be missing?
So I think one aspect that we haven't really touched is the how we use dark energy to define time, right? So I don't know if you want me to go into that, but I could try and summarize that briefly.
Sure, absolutely. I think it
Um,
might be useful.
yeah. So usually, so I mean these questions, of course, have been there for a long time. So what happens to the singularity, inside a black hole? Can quantum mechanics say something about that? And one of the things that's usually a stumbling block is the difference at which time is defined in these theories. So in quantum mechanics, as I said in the beginning, there's kind of usually kind of an absolute notion of time. You have your system in your lab, you're preparing some kind of initial state, and it evolves in time, and then later on maybe you make some kind of measurement. But in relativity, it's general relativity, it is a very observer-dependent concept. So somehow you need to have a preferred notion of time so that you can relate it to quantum theory, which does need a notion of time to tell you what's happening in the future, right? So in a sense, there's a fundamental clash there, that in one theory, time is essential to even define the theory, and in relativity, it's sort of more a secondary thing. Once you know who you are in the universe, then you can talk about time, but the universe is kind of independent of that, if that makes sense. So that's basically the key new idea here, that we kind of use a standard of time that depends on the dark energy in the universe. So dark energy is this mysterious form of energy that we don't really understand very well, which leads to an accelerated expansion of the universe. So we kind of think it's actually there, but we don't really understand it very well. And basically, if you have a source of energy in the universe, you can use it as a very abstract type of clock, in a sense. So you measure the flow of time kind of relative to this dark energy that's everywhere in the universe. And so that's kind of the new idea here, really. That sort of you use this kind of standard of time, which is related to the existence of the dark energy.
Stefan Gielen, thank you so much for taking the time to speak with me. I appreciate it.
Thank you. It was a pleasure.
Stefan Gielen is a senior lecturer at the University of Sheffield. His team's research is published in the journal Physical Review Letters. This is The Best of Our Knowledge. I'm Lucas Willard. Oregonians are well aware of the water that flows in rivers from the Cascades, but researchers seeking to learn more about the mountain range in the Pacific Northwest have determined that a giant aquifer locked in the rock of the mountainous region could be 3 times the size of Lake Mead, America's largest freshwater reservoir. To learn more about their study, I spoke with Leif Karlstrom, an earth scientist at the University of Oregon.
The Cascades are a volcanic mountain range, right? The reason that we have these mountains here is fundamentally because of the long-lived, and when I talk about long-lived, I'm talking about like millions of years volcanic activity. And that, that's the volcanoes all the way from Canada down to Northern California, associated with the Cascadia subduction zone. And so we want to think of those really as what's driving everything in the system. And that's how this study started, actually, was to try to understand the landscape that's represented by these mountains. One of the co-authors on our study, Kathy Cashman, has this wonderful analogy, which is that in the Cascades and like landscapes like it, you essentially have like a fight between two of the most important geological fluids that exist, water and magma. And they're like two sumo wrestlers that are squaring off, right? And sometimes one pushes one a bit, and the other sometimes the one pushes the other, but they're more or less equals. And that's really what you want to think about when you think about the Cascades or any volcanic landscape, is the sort of long-term construction of the landscape by yes, lava flows and eruptive deposits, but also by the sort of swelling up of the ground, and then water, climate that's infiltrating, that's eroding, that's carving river valleys and channel networks. And it's really the interplay of those things that we were studying, trying to understand, why the landscape looks the way it does, essentially.
Did you gather any understanding as to what led to the formation of this very large aquifer?
Yeah, so I guess what you want to think about for the Cascades, like I said, this has been a mountain range that's been volcanically active for a long time. And I live in Eugene, which is actually just west, I guess, of our study area. And if I'm at my house in Eugene, I sometimes like to think about the the volcanism that was once active here. The same volcanism that's building the mountains currently was active in Eugene, quite a bit to the west, about 30 million years ago. And so progressively since that time, the volcanism has sort of migrated east. And that is also something that's pretty important for our study, because what that gives us is a sort of a very clear change in the age of the bedrock, such that when we get to the tops of the mountains now, there's active volcanoes, right? There's magma underneath the region that we're studying at present day. In fact, we can measure its movements. And that magma and the sort of repaving of the landscape by lava flows over and over the last, say, millions of years has resulted in a certain structure of the bedrock. That structure is essentially defined by lava flows that have sort of in their interior these very small cooling joints, and at their tops and bottoms, large permeability channels, if you want to think about that way. And it's this sort of like interplay between those vertical small fractures and the lava flow tops and bottoms, which governs how water moves. And so we also have a lot of rain in the Pacific Northwest, and that rain and snow, when you get up to the mountains, is infiltrating into this stack of lava flows. And that's generally, I guess, how I would conceptualize the aquifer up there.
So how do you actually estimate the size of the aquifer? Is it as simple as looking at a map and studying where water is flowing from, or is it more complicated than that?
Well, I should say that we didn't discover this aquifer. It's well known. In fact, people, I think, for thousands of years have been using this water. It's something that scientists have been interested in for the last couple of decades, but they've largely been approaching it from a, I would say, more traditional hydrology standpoint, where you sort of look at what's coming out of the ground. And there are some massive spring systems in this area that really point to this remarkable size of this aquifer. Individual springs that could, for example, supply the entire Portland, Oregon metro area in perpetuity. Just like truly massive springs. And so previous work has used those springs to estimate the size of the aquifer that must be feeding them. What we did is actually we took a slightly different approach. We used old geothermal exploration drill holes, which, backstory on that, this is a volcanic mountain range, so there's good chance that there's extra heat in the region. And so in the 70s and 80s, there was a lot of interest in geothermal resource potential. And so a number of these holes were drilled. And that's, fairly unusual. It'd be really expensive today, essentially impossible, but it gives you a direct look at what's in the subsurface. And what they found was unfortunately not geothermal potential, but rather a signature of groundwater. They saw that the temperatures as you drilled into the earth did not get hotter as expected at all. In fact, they sort of stayed at near or even below surface temperatures down to kilometer depths or more. And really the only way that can happen is if you have downward infiltrating groundwater that's sweeping away the heat that would otherwise cause the temperatures to increase. So we use those geothermal drill holes more or less as a direct fingerprint of where the water is currently, and then use their spatial distribution to essentially map it. And so we have a picture. It's a bit of a fuzzy picture because we're constrained by the number of the holes that exist currently. But we nonetheless have a pretty good idea of where the water is and how much there is.
And that's a lot larger than originally anticipated, correct?
Yes, we increased the estimate, I guess, of the active groundwater reservoir here by about 3 times.
Wow.
So yeah, it's a tremendous amount of water, about almost 3 times the volume of Lake Mead, if you want to think about it as a reservoir. This is not a big lake, of course, right? So that water is hosted in fractures and so forth. So it is quite different, but it is a massive groundwater reservoir. Yeah.
So with this new research and this new estimate for a size, does that have any applications when it comes to either drinking water protection. Where do you think this study and the results of this study will be applied?
Well, I guess the first thing's to say, of course, that our study is much broader than water. So, just to reiterate that, we really are interested in the origins of this landscape. And so I think some of our results here are sort of scientifically perhaps most important in that context. Of course, the water resource is incredibly important, and it's already being used, right, on both sides of the Cascade Crest, right? This aquifer is feeding the Deschutes River, for example, to the east, and the McKenzie River and the Willamette River. It supplies, a large fraction of the water coming to the Columbia and to Portland in summer when there's no rainfall. For example, the McKenzie River alone is about 40% of the Willamette River flow in summer. So a tremendous amount given how big the Willamette River is. And so I guess one thing to say is simply that, in some sense, this isn't free water. We're already using it. And I guess going forward, right, making intelligent decisions or sort of decisions about its management, I think will benefit from just knowing how much water is there, right? If you're managing a resource, first thing you'd like to know is how much there is, and then of course you'd like to know, what's coming in, what's coming out, the fluxes. But there weren't really robust estimates for the volume at all before this, and I would say that there's still some work to be done on this. Actually, I mentioned that our picture is pretty good, but it's fuzzy, and so I think there's a lot more work to be done to really assess what's there, and then further to assess its sensitivity, because we know, for example, that there's decreasing snowpack over the last, say, 30 years, and that's projected to increase by quite a bit due to climate change. And as a result, we'd like to know, the sensitivity of this aquifer to perturbations like that.
Fascinating. Well, thanks so much for taking the time. I appreciate it.
Thank you.
Leif Karlstrom is an earth scientist at the University of Oregon. His research is published in the Proceedings of the National Academy of Sciences. This is The Best of Our Knowledge. I'm Lucas Willard. If you'd like to tell the best of our knowledge what you think, send us an email at knowledge@wamc.org. You can listen to The Best of Our Knowledge anytime as a podcast, downloadable wherever you get your podcasts. If you want to catch up on past episodes or hear more WAMC National Productions programs on the news, academic study, books, women's issues, the media, and the environment, visit wamcpodcasts.org. This has been The Best of Our Knowledge, episode 1801. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. Thanks to associate producer Madeline Reynolds. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, wamc.org. Until next time, I'm Lucas Willard.